All right, let's dive into custom data structures. We're going to base this deep dive on a blog post from Algo Academy. It's their cheat sheet for mastering this stuff.
Mastering custom data structures, huh? It's like unlocking a secret level in programming. You can write code that's not just good, but amazingly efficient,
Yeah.
powerful.
Okay, I'm listening.
Yeah.
But why even bother with custom structures when we've already got, built-in ones? Isn't that kind of like reinventing the wheel?
Well, sometimes, the standard wheel just doesn't quite cut it. You wouldn't use a monster truck to win a Formula One race, right? You got to have the right tool for the job.
Custom data structures are like fine-tuning your tools, I guess, for peak performance. I see the appeal. So where do we begin?
Algo Academy lays out 4 golden rules for designing them: abstraction, encapsulation, modularity, and efficiency.
Okay, let's break those down. Abstraction first. What's the gist?
Okay, imagine your car's dashboard. You don't need to know how the engine works to drive, right?
Yes.
Abstractions like that, it hides those messy details behind a nice, clean interface. You just get the essential controls without all the complexity.
So it's about keeping things user-friendly, even for the programmer. What about encapsulation?
Now we're popping the hood and looking at the engine itself. It bundles data and the methods that operate on that data together in one neat package. It protects the data and makes your code way easier to maintain.
So it's like a self-contained unit.
Yeah.
Keeping things organized and preventing any code clashes.
Got it. Now, modularity, that sounds a bit like playing with Legos.
Yeah, you got it. Just like Legos. Modularity means breaking down your data structure into smaller, independent pieces. You can reuse these pieces, swap them out, makes your code flexible and manageable.
Okay, so it's about creating a system that's adaptable and easy to work with. And lastly, efficiency, making sure your code runs like a well-oiled machine writer.
Exactly. Optimizing for time and space complexity. You want your structure to be fast and use memory wisely. So those are the 4 pillars of good design. But how do we actually build these custom structures? This post mentions composition and inheritance as techniques.
Right, let's start with composition. Imagine building furniture. You take legs, a tabletop, screws, individual parts, and combine them into something new. Compositions like that. You take existing data structures, combine them in clever ways, and you've got your custom structure.
Like building a custom solution from pre-made components. The blog post actually has the Python code example.
Yes, it shows how to build a linked list. Each node in the list is its own object, and you link them together.
Each node is like a link in a chain, and we can control how they connect and what data they hold. Pretty cool. But inheritance, how does that work?
Inheritance is more like creating a specialized version of an existing blueprint. You take a pre-existing structure, like an array or a list, and you extend it. New features, new behaviors.
So it's like taking a basic car and souping it up into a high-performance sports car. You keep the basic structure, but add specialized components.
Perfect analogy. And the post has a C++ example, a generic stack built using inheritance. Can hold any type of data, super flexible.
So we've got composition for building from scratch and inheritance for specializing existing structures. But what about when we need to get, really smart with memory management, especially in languages that don't do it automatically?
That's where it gets interesting. We can use specific techniques to get the most out of our code by controlling how memory is allocated and deallocated.
Okay, you've got my attention. What kind of techniques?
The post focuses on 3: custom allocators, memory pools, and smart pointers. Custom allocators, they give you fine-grained control over memory assignment. Think of them like a personal shopper for your data's memory needs.
That's a great analogy. So what are memory pools?
They're like reserving a block of parking spaces just for your data. You pre-allocate memory, manage it internally, much faster than constantly asking the OS for more.
Dedicated parking for your data. No
Yeah.
more circling the lot. And there's a C++ code example, right?
There is. It shows a simple but efficient implementation.
And what about smart pointers?
Think of them like a self-cleaning system for your memory. They keep track of how many references point to a piece of data, and when the count hits 0, poof, data's cleaned up automatically.
That's useful, especially for C++A, where you normally have to manage memory manually.
Right.
Okay, so besides memory management, the post also mentions lazy initialization and copy on write as optimization techniques.
Yeah, those are fantastic for boosting performance in certain situations. Lazy initialization, it's like waiting to order dessert until you've finished your main course. You delay creating an object until you absolutely need it.
I can relate to that. So you avoid unnecessary work if you don't end up needing it. What about copy on write?
It's like sharing a document but only making a copy when someone actually makes a change. Perfect for large data structures that are read often but rarely modified.
So it's all about saving time and resources by only copying when absolutely necessary.
Very clever. Now let's talk about thread safety. This is crucial when we're in multi-threaded environments, where multiple threads can access the same data structure concurrently.
Exactly. It's like having multiple chefs trying to cook in the same kitchen at the same time, without any coordination. Chaos.
So how do we make sure our custom data structures can handle that chaos?
We need to make them thread safe. Ensure operations on the data are atomic and access is synchronized. The post gives a good example of a thread safe queue in C++s.
How does it achieve that thread safety?
It uses a mutex. Think of it like a lock on a single-lane bridge. Only one thread can hold the lock at a time, prevents collisions, ensures things happen safely, orderly.
So the mutex is like a traffic controller. Make sure everyone takes turns.
Exactly. And it also uses something called a condition variable. Acts like a signal, letting threads know when the queue's empty or full, no more pointless waiting. So it's a combination of controlled access and smart signaling to keep things running smoothly in a multi-threaded environment. Now, this post also teases us with some advanced custom data structure implementations.
Yes, it showcases 3: trie, LRU cache, and segment tree. Let's start with trie. Imagine you're building autocomplete for a search engine. You need a way to store and retrieve a huge dictionary of words, fast. That's trie.
So it's like a specialized dictionary built for speed,
Yeah.
especially when you're dealing with lots of prefixes.
Exactly. It's structured like a tree, but instead of whole words in each node, it stores individual characters.
So if I'm searching for apple, each letter A, P, P, L, E is a node in the tree.
You got it. You traverse the tree, following the path of letters, and the post even includes a Python code example, shows how to build this structure and use it for searching.
Wow, so this tree-like structure makes searching so efficient. No more comparing whole words, just following a path of letters.
Yeah.
What about LRU cache?
LRU stands for least recently used. It's all about managing a limited amount of memory as efficiently as possible. Think of it like an exclusive club with a fixed number of spots. To let a new member in, you got to kick out the least popular one, the one who hasn't been around in a while.
So it's all about keeping the hottest data readily available and getting rid of the stale data to make room. Where is this kind of cache used in the real world?
Everywhere. Web browsers, operating systems, databases, anywhere you need to keep frequently accessed data in a fast access cache. The post gives a C++ example, combines a hash map and a doubly linked list to do this.
So it's a combination of quick access and a clever eviction strategy. And lastly, let's talk about the segment tree. This one sounds a bit complex.
It is, but it's really powerful when you need to run queries on ranges of data. Imagine you've got a giant array of numbers and you want to find the sum of a specific section of that array.
So it's like a turbocharged array that can answer range-based questions quickly.
Exactly. And it can handle more complex queries too, like finding the minimum or maximum value in a range. The post has a Java implementation to show how it works.
Wow, these advanced structures sound incredible. I'm seeing how custom data structures can really take your coding to the next level. But before we wrap up this part, the blog post also has some best practices for implementation.
Absolutely. It talks about clear documentation, rigorous testing, performance benchmarking, code review, and iterative refinement. These are fundamental, and they become even more important when you're dealing with the complexity of custom data structures.
Right, because well-documented and thoroughly tested data structure is a joy to work with, but a poorly designed one, that can be a nightmare. The post breaks it down into 5 key practices. Can you give us a quick rundown?
Sure. First, documentation. You got to clearly explain the purpose, usage, performance of your custom data structure. Think of it like writing a user manual.
Documentation. Often overlooked, but it can save so much time and frustration down the road. What about testing?
Testing is crucial. Got to make sure it works correctly in every situation, including edge cases. This might involve writing unit tests to cover various scenarios and verify the expected outcomes.
And then there's performance benchmarking.
Yeah, it's all about measuring how it performs in real-world situations, how it behaves under different loads, how it compares to other implementations, helps you find bottlenecks and optimize.
So it's not just about making it work, but making it work well. What about code review?
Code review. It's like a fresh set of eyes. Another developer looking at your code, they can help catch bugs, improve readability, suggest different approaches. Always good to get feedback.
And finally, iterative refinement. I'm guessing that's about recognizing that no code is ever truly finished and being open to continuous improvement.
Exactly. As you use it, you might find areas for improvement. Performance, functionality, design. You've got to be open to tweaking and refining based on real-world feedback.
So it's a continuous cycle of learning and improvement. We've covered a lot of ground in this part. Explore the why, the how, and the best practices of custom data structures. But I'm ready to see these things in action.
Me too. And that's exactly what we'll do in the next part of our deep dive. We'll take a closer look at those advanced implementations. Try, LRU cache, and segment tree, and see how they solve real-world problems.
Okay, let's jump back into custom data structures. You know, we talked about the basics, best practices, but now I kind of want to see how these things work, in real life. We touched on those advanced implementations last time. Try, LRU cache, and segment tree. Ready to dive into those.
Yeah, absolutely. This is where it gets exciting. They might sound complex, but they're really just built on the same principles we've been talking about. Let's start with try, or sometimes it's called a prefix tree. Remember how we talked about autocomplete in search engines?
Yeah.
Classic try use case.
Right. Try is all about, efficiently storing and searching strings, especially when you have lots of prefixes, like a supercharged dictionary, but built for speed.
Exactly. Imagine a search engine having to go through billions of pages every time you start typing. A try is, it's built for that. Instead of storing whole words, it uses this tree structure where each node is a single character.
So like if I search for apple, each letter, A-P-P-L-E, each one is a separate node.
Yeah.
And as I type, the search narrows down based on the path I'm taking through those letters.
That's it. And the Algocademy post, it actually has a Python code example that shows you how to build this. You insert words into the try, and then you can search for, complete words or just prefixes. Perfect for those autocomplete suggestions.
It's amazing how this tree structure makes searching so efficient,
Yeah.
You're not comparing whole words, just like following a path. It's like a choose your own adventure, but for search.
Yeah.
Okay, what about LRU cache? That one still sounds kind of mysterious to me.
LRU stands for least recently used. It's all about making the most of limited memory. Imagine you've got this VIP room, right? But only a few spots. When a new guest comes in, someone has to leave. In an LRU cache, the one who gets kicked out is the one who hasn't been accessed in the longest time.
Oh, okay. So it's like this constant game of musical chairs where the least popular data gets booted when space runs out. But how does it even keep track of what's been accessed recently?
Pretty clever, actually. It uses a hash map for fast lookups, but it also uses a doubly linked list to keep track of the order things have been accessed. The hash map lets you find what you're looking for instantly, and the linked list, it keeps track of who's been in that VIP room the longest. The C++ example in the post shows this in more detail.
So if I access a piece of data, it gets bumped to the front of the line, like a VIP getting special treatment. And the one at the back, the least recently used, is the one who gets the boot.
Exactly. It's simple but really effective for managing a cache, when space is limited. Okay, ready for the big one, the segment tree.
Yeah, hit me.
This one's a bit more complex, but it's super powerful when you want to run queries on specific ranges of data. Remember we talked about finding the sum of a section within a giant array?
Yeah.
Imagine trying to do that with a million numbers. Going one by one would take forever. A segment tree, it takes a different approach. It pre-calculates and stores the sums of smaller chunks of the array. And it does this in a tree structure.
So it's like breaking a huge problem down into smaller ones and storing the results in a way that makes it really fast to retrieve.
Yeah, exactly. And it's not just sums. You can use it to find the minimum, maximum, or other values within a range. The post has a Java example that shows how this tree is built and used.
This sounds like a secret weapon for data analysis. I can see how this would be so useful when you've got massive data sets and need quick answers to these range-based questions.
Definitely a powerful tool. And really, try LRU Cache and Segment Tree are just a few examples. There are tons of others out there, each one designed for something specific.
It's amazing how these like kind of abstract concepts can be applied to real-world problems. But I got to admit, I'm still wrapping my head around how this all impacts,
Mhm.
our everyday lives. We're using these things all the time, but they're kind of like invisible, right?
It's true. They are kind of invisible, working behind the scenes, silently powering so much of our digital world. But once you start noticing them, you see them everywhere.
Yeah, everywhere. Like, take search engines. Remember we were talking about try being perfect for autocomplete? Every time you type something into Google, a try structure is helping suggest those completions, those related terms, going through billions of web pages super fast.
It's like Google can read my mind, you know?
Well, at least it feels that way thanks to try. And what about social media? I don't think those endless scrolling feeds would even be possible without, you know, some really clever data structures working behind the scenes.
Absolutely. Social media platforms, they rely so heavily on custom data structures to manage tons of user data, posts, connections, all those interactions. LRU caches, they're used to keep the most popular content ready to go, so the experience is smoother and more responsive.
They're like anticipating what I want to see, serving up content before I even know I want it. It's kind of impressive, but also a little creepy.
That's the power of well-designed data structures, I guess. They make these complex things seem so simple. Think about online shopping. Those recommendation engines that suggest products you might like. Those are often using custom data structures to track your browsing history, what you buy, what you like.
So those suggestions aren't just random. It's all calculated, guided by algorithms and data structures that understand my shopping habits.
Exactly. And how about navigation apps like Google Maps or Waze? They use sophisticated algorithms, custom data structures to figure out the best route. They take into account traffic, road closures, even how you like to drive.
It's like having a personal navigator, constantly crunching numbers, guiding me through all those roads. It's amazing how this technology has become such a seamless part of our lives.
Yeah, it is. It's really a testament to computer science, the ingenuity of the developers who create these things. But it's important to remember these tools, they're not inherently good or bad. They can be used for both. It's up to us to understand them, and advocate for how they're used.
You're right. That's a really important point. As we rely more and more on technology, we need to be aware of the impact and advocate for ethical development. But let's not dwell on that too much. The world of custom data structures, it's full of creativity, so much potential. It's always evolving, new challenges, new discoveries.
Absolutely. Who knows what amazing applications we'll see in the future, all powered by this creative use of data. Maybe self-driving cars that use custom data structures to navigate structures we haven't even imagined yet.
It's amazing. The possibilities are endless. That's what makes this whole field so fascinating.
Well, I think that about wraps up our deep dive into custom data structures. Hopefully, you've got a new appreciation for these forces that shape our digital lives.
I definitely do. And to everyone listening, the next time you're on your favorite app or website, take a second to think about those data structures working behind the scenes. It's a whole world of hidden wonders just waiting to be explored.
Keep exploring, keep learning. See you next time.